Hello, hello, hello. Let's start our next reading. We did great yesterday. Today we're starting a little late because it's going to be 8 p.m. US, 9 local. But we're going to read those pages. And we stopped on page 107, iterating, let's see, applying enhanced for loop. In fact, I think we did part of page 8, 108. Okay, so let me put move this out of the way here. All right, here we go. All right, so let's get started. We're going to start at the beginning of page 108, just for the sake of. Oh yeah, this is where we started here, but this is where we stopped. So let's start at the beginning of page 108. Okay, so that we can have a more specific point of reference here for this video. All right, maybe I can make this bigger. No, too much. All right. Okay, very well. So, local variable type inference in a for loop. Okay, I got a window, I got a mobile. Excuse me. Let's move this out of the way. Much better. Okay, excellent. All right, here we go. Okay. Local variable type inference in a for loop. I have running notes, so I'm sorry. As explained in chapter 3, JDK 10 introduced a feature called local variable type inference, which allows the type of a local variable to be inferred from the type of its initializer. To use the local variable type inference, the type of the variable is specified as var, and the variable must be initialized. Local variable type inference can be used in a for loop when declaring and initializing the loop control variable inside a traditional for loop, or when it's second, okay, or when specifying the iteration variable in a for each or loop. The following program shows an example for each case. Okay, let me briefly mute the mic. Excuse me a second. All right, use type inference in a for loop. Class times inference. Okay, so I already know this kind of thing, so I'm just gonna show the code for the sake of the video, but I'm not gonna stop here. So you can pause the video. In this example, loop control variable x in this line is inferred by the type to be the type double because that is the type of its initializer. Iteration variable v is this line. Inferred to be of type int because that is the elementary type of the array nums. Interesting point. One last point. Because a number of readers will be working in environments that predate JDK 10, local variable type inference would not be used by most of the for loops in the remainder of this edition of this book. You should, of course, consider it for new code that you write. Okay. Oops. Here we go. Nested for loops. Oh, by the way, I have to stop at 38, page 38, 138. Nested for loops. Like all other programming languages, Java allows loops to be nested. That is, one loop may be inside another. For example, here is a program that nests for loops. All right, I already know this, so just, and we already seen this to the pages, so just pause the video if you like. Okay, the output is produced by this program is shown here. Okay, this is the output. Okay, jump statements. Java supports three jump statements: break, continue, and return. These statements transfer control to another part of your program. Each is examined here. In addition, note, in addition to the jump statements discussed here, Java supports one other way that you can change your program's flow of execution through exception handling. Exception handling provides a structured method by which runtime errors can be trapped and handled by your program. It is supported by the keywords try, catch, throw, throws, and finally. In essence, the exception handling mechanism allows your program to perform a non-local branch. Since exception handling is a large topic, it is discussed as its own chapter, chapter 10. And that is really an interesting subject. Using break. In Java, the break statement has three uses. First, as you have seen, it terminates a statement sequence in a switch statement. Second, it can be used to exit a loop. Third, it can be used as a civilized form of goto. The last two uses are explained here. So we already see the one. Okay. Using break to exit a loop. By using break, you can enforce immediate termination of a loop by passing the conditional expression and any remaining code in the body of the loop. Okay. When a break statement is encountered inside a loop, the loop is terminated and program control resumes at the next statement following the loop. Here is a simple example. Again, I already know this, so this is for the sake of the video. And just please pause it and we can continue later. Okay, so here is the output. Alright. Excuse me. As you can see, although the for loop is designed to run from 0 to 99, the break statement causes it to terminate early when I equals 10. The break statement can be used with any of Java's loops, including intentionally finite infinite loops. For example, here's the preceding program coded by use of a while loop. The output from this program is the same as just shown. Break loop 2, okay. If break, terminate the loop, okay. When used inside a set of nested loops, the break statement will only break out of the innermost loop. For example, and here's the code again. Okay. So the break will terminate of loop, the for loop j. The program generates the following code, and here it is. As you can see, the break statement in the inner loop only causes termination of that loop. The outer loop is unaffected. Pretty good point. Here are other points to remember about break. First, more than one break statement may appear in a loop. However, be careful. Too many break statements have the tendency to destructure your code. Second, the break that terminates a switch statement affects only that switch statement and not any enclosing loops. We only stops the switch, basically breaks out of the switch. Remember, break was not designed to provide normal means by which loop is terminated. The loop's conditional expression serves this purpose. The break statement should be used to cancel a loop only when some sort of special situation occurs, using break as a form of go-to. Okay. In addition to its uses with the switch statement and loops, the break statement can also be employed by itself to provide a civilized form of the go-to statement. Java does not have a go-to statement because it provides a way to branch in an arbitrary and unstructured manner. This usually makes go-to written code hard to understand and hard to maintain. It also prohibits certain compiler optimizations. There are, however, a few places where the go-to is a valuable and legitimate construct for flow control. For example, the go-to can be useful when you're exiting from a deeply nested set of loops. To handle such situations, Java defines an expanded form of the break statement. I think this is the label break statement that he's going to talk about. By using this form of break, you can, for example, break out of one or more blocks of code. These blocks need not be part of a loop or a switch. They can be any block. Further, you can specify precisely where execution will resume because this form of break works with the label. You see? As you will see, breaks gives you the benefits of a go-to without its problems. Yeah, I knew it was the labels. I really liked using that too. The general form of the label break statement is shown here. Break, label. Basically, you give it the name. The label is the name that you give it. Most often, label is the name of a label that identifies a block of code. This can be the standalone block of code, but it can also be a block that is the target of another statement. When this form of break executes, control is transferred out of the named block. The labeled block must enclose the break statements, but it does not need to be the immediately enclosing block. This means, for example, that you can use a label break statement to exit from a set of nested blocks, but you cannot use break to transfer control out of a block that does not enclose the break statement. Yeah, that's true. To name a block, put a label at the start of it. A label is any valid Java identifier followed by a colon. Once you have labeled a block, you can then use this label as the target of a break statement. Doing so causes execution to resume at the end of a labeled block. For example, the following program shows 3 nested blocks, each with its own label. The break statement causes execution to jump forward, past the end of the block labeled second, skipping the 2 println statements. Let's look at this. I like using this. Again, for the sake of the video, I'm not gonna pause and analyze the thing, because I already know. Just pause the video. Okay, using break, class break. Okay, boolean t is true. First, second, third. System out, print library for the break. If t break second. Okay. Okay, break out of the second block. Well, execute. This one execute. There you go. Running this program generates the following output. Before the break, this is after the second block. Okay, and by the way, this is the second block. That's after the closing bracket for the second block. Okay. One of the most common uses for a labeled break statement is to exit from nested loops. For example, in the following program, the outer loop executes only once. Using break to exit from nested loops. Okay, again, here's the program. break outer. Yep. All right. And here's the code. Yeah. Okay. Pause and see. All right. Let's bring it up. As you can see, when the inner loop breaks to the outer loop, both loops have been terminated. Notice that this example labels the for statement, which has a block of code as its target. Keep in mind that you cannot break to any label which is not defined for an enclosing block. For example, the following program is invalid and will not compile. All right. Class break error. All right. Here's the break. First label is 1. Okay, for the break 1. Okay, yeah. So the break for 1 with the label 1 is pointing to the wrong block of code, which is the second block of code and not the first one that it was assigned to. Yeah. Since the loop label 1 does not enclose the break statement, it is not possible to transfer control out of that block. Alright. Using continue. Sometimes it is useful to force an early iteration of a loop. That is, you might want to continue running the loop but stop processing the remainder of the code in its body for this particular iteration. That's like a skip. This is, in effect, a go to just pass the body of the loop to the loop's end. The continue statement performs such an action. In while and do while loops, a continue statement causes control to be transferred directly to the conditional expression that controls the loop. In a for loop, control goes first to the iteration portion of the for statement and then to the conditional expression. For all 3 loops, any intermediate code is bypassed. Here's an example program that uses continue to cause 2 numbers to be printed on each line. All right, let's look at the first part. Class continue. All right, first part of code. You can pause the video, of course, because I already know this. Continue. Basically, it's going to skip the system out. Print line. This code uses the modulus operator to check if I is even. If it is, the loop continues without printing a new line. Here's the output of this program. Yep. As for the break statement, continue may specify a label to describe each enclosing loop to continue. Okay. Here's an example program that uses continue to print a triangular multiplication table for 0 through 9. Now, see, that's interesting because I never thought to use a continue with a label. Or maybe once, actually. But not something that I kept in mind. So this is pretty good to read through. Okay, continue with label. Outer. Look at that. The continuous label with the outer label. Oh, that is nice. But that means that it will skip the rest of the for loop for the j variable, and it will go back to the for loop for the I variable. That is pretty interesting. That is a very interesting program. Nice. The continue statement in this example terminates the loop counting j and continues with the next iteration of the loop counting I. Here's the output of this program. That's pretty nice. In fact, I think I want to, give me a second. We're going to, here we go. Okay, so I'm gonna pause this only because you can see the mouse, but you don't see TextMate, so I have to like reload it into the system. Give me a second. Um, and we're back. Okay, so let's create a new window. Oops. There you go. Let's save this one. Okay. I want to save this program because this one is interesting. I might even try to code it myself without remembering this because I find it so nice. Such a cool idea. Let's make it bigger. Alright, and let's bring this Java. Okay, let's save it. Okay. Yep. You know what? Let's run it since we're already here. Excuse me. And there it is. Pretty cool. All right. Let's get another one open already and close this one. All right. Let's get it ready. Cool. All right. Okay, good uses of continue are rare. Rather reason is that Java provides a rich set of loop statements which fit most applications. However, for those special circumstances in which early iteration is needed, the continue statement provides a structured way to accomplish it. The return. The last control statement is return. The return statement is used to explicitly return from a method. That is, it causes program control to transfer back to the caller of the method. Ooh, that's a nice way to put it, actually. I never thought of it like that. Oof, I'm loving this book. So as such, it is categorized as a jump statement. Although a full discussion of return must wait until methods are discussed in Chapter 6, a brief look at return is presented here. At any time in a method, the return statement can be used to cause execution to branch back to the caller of the method. Thus, the return statement is immediately terminates the method in which it is executed. Hmm. The following example illustrates this point. Here, return causes execution to return to the Java runtime system, since it is the runtime system that calls main. So is he saying that this return statement can be used midway through the body of a method? I never thought of that. I gotta try that. Gotta test that. Hmm. Okay, demonstrate return. Class return. Let's see what he's gonna do here. Oh yeah, look at that. He's using it halfway. You see that? If T return to caller, and the printf statement is not going to, it's not going to run. Hmm, that's pretty cool. Okay, the output from this program is shown here. Okay, before the return. As you can see, let's bring it up. Halfway through the screen is better. Okay. As you can see, the final println statement is not executed. As soon as a return is executed, control passes back to the caller. One last point. In the preceding program, the if T statement is necessary. Without it, the Java compiler will flag an unreachable code error because the compiler will know that the last println statement will never be executed. To prevent this error, the if statement is used here to trick the compiler for the sake of this demonstration. Okay. Okay, so this is the main method. System print line. If t true, return. Wait a minute. This is pretty good. I just realized that this was a little deeper than I even noticed. Here, return causes execution to return to the Java runtime system, since it is the runtime system that calls the main method. Oh, that's beautiful. Oh, that's beautiful. Oof. So it returns one layer of abstraction back, only one. So if it was another method calling it, it will return to that method instead. Ooh, that's pretty good. Hmm. That's why he makes that declaration. Okay, this page is intentionally blank. Yay! We reached the first blank page. All right. Oof, chapter 6. Let's go. All right, I can. Okay, chapter 5. Here we go. And let's open chapter 6. All right. Introducing classes. Okay. The class is at the core of Java. Excuse me. It is a logical construct upon which the entire Java language is built because it defines the shape and nature of an object. Sure. As such, the class forms the basis for object-oriented programming in Java. Any concept you wish to implement in a Java program must be encapsulated within a class. Because the class is so fundamental to Java, this and the next 3 chapters will be devoted to it. Here, you will be introduced to the basic elements of a class and learn how a class can be used to create objects. You will also learn about methods, constructors, and this keyword. Okay, so I'm pretty familiar with how classes work, so I'm just gonna read through it. I'm not gonna spend much time on the programs. Just post the video where you need it. Now the keyword is a confusing concept here, so that's gonna be nice to review. Okay, so class fundamentals. So class fundamentals. All right. Classes have been used since the beginning of this book. However, until now, only the most rudimentary form of a class has been shown. The classes created in the preceding chapters primarily exist simply to encapsulate the main method, which has been used to demonstrate the basics of the Java syntax. As you will see, classes are substantially more powerful than the limited ones presented so far. Perhaps the most important thing to understand about a class is that it defines the new data type. Once defined, this new type can be used to create objects of that type. Thus, a class is a template for an object, and an object is an instance of a class. Yep. Because an object is an instance of a class, you'll often see the two words object and instance used interchangeably. Okay. The most important thing to understand is that a class defines a new data type. Yep. Okay, the general form of a class. When you define a class, you declare its exact form and nature. You do this by specifying the data that it contains and the code that operates on that data. While very simple classes may contain only code or only data, most real-world classes contain both. As you will see, a class code defines the interface to its data. Yep. A class is declared by use of the class keyword. The classes that have been used up to this point are actually very limited examples of its complete form. Classes can and usually do get much more complex. A simplified general form of a class definition is shown here. All right, excuse me, I'm gonna pause. All right. So class keyword, class name, type instance variable one, type instance variable two, which are actually called fields. Type method name, it's a class called a class method. Uh, type method name two, parameter list, body method, okay, method n, and so on. Okay. The data or variables defined within a class are called instance variables. The code is contained within methods. Collectively, the methods and variables defined within a class are called members of the class. In most cases, the instance variables are acted upon and accessed by the methods defined for that class. Thus, as a general rule, it is the methods that determine how a class data can be used. Okay. Variables defined within a class are called instance variables because each instance of the class, that is, each object of the class, contains its own copy of these variables. Thus, the data for one object is separate and unique from the data for another. We will come back to this point shortly, but it is an important concept to learn early. Yeah, that's because whenever you call the object that uses those variables, you don't inherit the data that was previously applied by another class to the same variable. Okay, all methods have the same general form as main, which have been used we have been using thus far. However, most methods will not be specified as static or public. Notice the general form of a class does not specify a main method. Java classes do not need to have a main method. You only specify one if that class is the starting point for your program. Further, some kinds of Java applications don't require a main method at all. A simple class. Let's begin our study of the class with a simple example. Here is a class called box that defines three instance variables: width, height, and depth. Currently, box does not contain any methods, but some will be added soon. Class box, double width, double height, double depth. In this case, they're instance variables. By the way, yeah, sometimes there's a difference when the use of the term fields because fields are uh, class variables meaning static, where they are the same no matter where that you use and they'll contain the same data. But that's a technicality anyway. All right. As stated, a class defines a new type of data. In this case, the new data type is called box. You will use this name to declare objects of type box. But it's important to remember that a class declaration only creates a template. It does not create an actual object. Thus, the preceding code does not cause any object of type box to come into existence. To actually create a box, you will use a statement like the following. Box, the name of the class. My box, the name of the actual object. And then new creates the space in the system for the box. And then box is a type of space that is created. So you create a variable, my box, of type box that can contain objects of type box, which are on the right, the new box part of the assignment. All right. After this statement executes, my box will refer to an instance of box. So my box, the variable of type box, will refer to an object of type box, or an instance, a copy of that object of that class. Thus, it will have physical reality. For the moment, don't worry about the details of this statement. Let's bring it up a little higher. As mentioned earlier, each time you create an instance of a class, you're creating an object that contains its own copy of each instance variable defined by the class. Thus, every box object will contain its own copies of the instance variable width, height, and depth. To access these variables, you will use the dot operator. The dot operator links the name of the object with the name of an instance variable. For example, to assign the width variable of my box the value 100, you will use the following statement. My box dot width 100. All right. This statement tells the compiler to assign the copy of width that is contained within the myBox object the value of 100. In general, you use the dot operator to access both the instance variables and the methods within an object. One other point. Although commonly referred to as the dot operator, the format specification for Java categorizes the dot as a separator. Okay. However, since the use of the term dot operator is widespread, it is used in this book. Yeah, I think that thinking of it as an operator makes more sense, because when you're importing a package, and when you're using methods like system.out.sprint, that operator is telling where to go next to find the information. Print that in out that in system. Anyway, I think that's a better use. Here is a complete program that uses the box. All right, and again, a complete program. I'm not gonna evaluate this program. Just pause the video if you need, please. Box, okay. Box demo. Box, my box, new box. My box with 10. Volume equals my box, that's my box, that's my box. Alright, that's pretty cool. Alright, let's bring that up. You should call the file that contains this program boxdemo.java, because the main method is in the class called boxdemo, not the class called box. When you compile this program, you will find that two .class files have been created, one for box and one for boxdemo. The Java compiler automatically puts each class into its own .class file. It is not necessary for both the box and the boxdemo class to actually be in the same source file. You could put each class in its own file called box.java and the boxdemo.java respectively. To run this program, you must execute boxdemo.class, and when you do, you will see the following output. Volume is 3000. Yeah. Excuse me. As said earlier, each object has its own copies of the instance variable. This means that if you have two box objects, each has its own copy of depth, width, and height. It is important to understand that changes to the instance variables of one object have no effect on the instance variables of another. For example, the following program declares two boxes. Is the thing that I was mentioning earlier. You get your own copy. Yeah. Alright, so box demo 2, again, for the sake of the video, I'll highlight it. You can pause it, but I don't have to do anything with it. Okay. The output produced by this program is shown here. As you can see, well, there we go. As you can see, my box 1's data is completely separate from the data contained in my box 2. Alright. Declaring objects. As just explained, when you create a class, you're creating a new data type. You can use this first type to declare objects of that type. You can use this type to create declare objects of that type. However, obtaining objects of a class is a two-step process. First, you must declare a variable of the class type. This variable does not define an object. Instead, it is simply a variable that can refer to an object. Second, you must acquire an actual physical copy of the object and assign it to the variable. You can do this using the new operator. The new operator dynamically allocates, that is, allocates at runtime memory for an object and returns a reference to it. Very important point, because variables for objects do not store the objects, only a reference to the object. And so when you're printing objects, say from like a collection, sometimes, or an array, sometimes what you're gonna have is the not the value will not print out, but the reference address will print out. So you gotta know how to work around that, but we're not gonna get to that now. The book is gonna explain that. Excuse me. This reference is essentially the address in memory of the object allocated by new. This reference is then stored in a variable. Thus, in Java, all class objects must be dynamically allocated. Let's look at the details of this procedure. In the preceding sample programs, a line similar to the following is used to declare an object of type box. My box in the box. This statement combines the two steps just described, and it can be rewritten like this to show each step more clearly. My box, declare reference to the object, and in my box, new box, allocate a box object. The first line declares my box as a reference to an object of type box. At this point, my box does not yet refer to an actual object. The next line allocates an object and assigns a reference to it to my box. After the second line executes, you can use my box as if it were a box object. But in reality, my box simply holds, in essence, the memory address of the actual box object. The effect of these two lines of code is depicted in figure 6.1. Okay, let's go ahead and find figure 6.1 first. Here we go. And then we'll go back and read. Okay, statement, my box, effect, my box. My box equals new box. My box gets the width, height, depth box object. Alright, so that's pretty cool. Okay, figure 6.1. Alright, so let's read. A closer look at new. As just explained, the new operator dynamically allocates memory for an object. In the context of an assignment, it has its general form, class var, new class name. Here, class variable is a variable of the class type being created. The class name is the name of the class that is being instantiated or created. The class name followed by parentheses specifies the constructor for the class. A constructor defines what occurs when an object of a class is created. Constructors are an important part of all classes and have many significant attributes. Most real-world classes explicitly define their own constructors within their class definition. However, if no explicit constructor is specified, then Java will automatically supply a default constructor. This is the case with box. For now, we will use a default constructor. Soon, you'll see how to define your own constructor. Briefly, a constructor is like a standard method that is empty. And each class needs at least one. So even though you didn't write it, it is invisibly there. And every time you create a new object, you're actually, in fact, using the constructor. So that class name right there, that's the constructor. Same as with the old codes here. Here in box, my box, new box, That's actually the constructor. You're just using the default one because you didn't change it. You didn't override it. Okay. Oops. Okay. So we saw figure 6.1. Let's keep reading. At this point, you might be wondering do why you do not need to use Noob for such things as integers or characters. The answer is that Java's primitive types are not implemented as objects. Rather, rather they are implemented as normal variables. This is done in the interest of efficiency. As you will see, objects have many features and attributes that require Java to treat them differently than it treats the primitive types. By not applying the same overhead to the primitive types that applies to objects, Java can implement the primitive types more efficiently. Later, you will see object versions of the primitive types that are available for your use in those situations in which complete objects of these types are needed. Those are the wrapper classes that he's talking about, that have the same names of the primitive types but in capital letters. It is important to understand that Noob allocates memory for an object during runtime. Yep. The advantage of this approach is that your program can create as many or as few objects as it needs during the execution of your program. However, since memory is finite, it is possible that Noob will not be able to allocate memory for an object because insufficient memory exists. If this happens, a runtime exception will occur. You will learn how to handle exceptions in Chapter 10. For the sample programs in this book, you won't need to worry about running out of memory, but you will need to consider this possibility in real-world programs you write. Yeah. Let's once again review the distinction between a class and an object. A class creates a new data type that can be used to create objects. That is, a class creates a logical framework that defines the relationship between its members. When you declare an object of a class, you are creating an instance of that class. Thus, a class is a logical construct. An object has physical reality. That is, an object occupies space in the memory. It is important to keep this distinction clearly in mind, like space in the physical memory of your computer. Assigning object reference variables. Object reference variables act differently than you might expect when an assignment takes place. For example, what do you think the following fragment does? It actually trespasses. Oh, excuse me. It actually transpasses the. Oh, wait a minute. Okay, it transpasses. Okay, here we go. It trespasses, or no, not trespasses. Passes over the information of the reference address, is, if I remember correctly. That's what that does. Okay. So basically, that's much better. All right. I wonder if I could get a bigger zoom. I'm gonna have to play around with the preview app a little later. You might think that B2 is being assigned a reference to a copy of the object referred to by B1. That is, you might think that B1 and B2 refer to separate and distinct objects. However, this will be wrong. Instead, after this fragment executes, B1 and B2 will both refer to the same object. That's right, because they have a copy of the same address. Because these variables do not contain the object, only the address, the reference to the object. So they both contain a copy of the same reference or address to the same object. The assignment of B1 to B2 did not allocate any memory or copy any part of the original object. It simply makes B2 refer to the same object as does B1. Thus, any changes made to object through B2 will affect the object to which B1 is referring, since they are the same object. Yep. The situation is depicted here. B1 and B2 refer to the same object. Yep. Excuse me. Although B1 and B2 both refer to the same object, they're not linked in any other way. For example, a subsequent assignment to B1 will simply unhook B1 from the original object without affecting the object or affecting B2. Yeah, because it's still B2 still contains a copy of the original reference. All right, B1 new book, B2 assign B1. B1 is null. B1 here has been set to null, but B2 still points to the original object. Basically, it still has the address. Remember, when you assign one object reference variable to another object reference variable, you're not creating a copy of the object, you're only making a copy of the reference. Absolutely. Alright. Introducing methods. Alright. Let's bring that up a bit, a little higher. Okay, much better to read. As mentioned at the beginning of this chapter, classes usually consist of two things: instance variables and methods. The topic of methods is a large one because Java gives them so much power and flexibility. In fact, much of the next chapter is devoted to methods. However, there are some fundamentals that you need to learn now so that you can begin to add methods to your classes. This is the general form of a method. Type, name, parameter, list, body of the method. Here, type specifies the type of data returned by the method. This can be any valid type, including class types that you create. If the method does not return a value, its return type must be void. The name of the method is specified by name. This can be any legal identifier. Oops. Other than those already used by other items within the scope. Okay, hold on, I misread that. So this can be any legal identifier other than those already used by other items within the current scope. Now that makes sense. Okay. The parameter list is a sequence of type and identifier pairs separated by commas. Parameters are essentially variables that receive the value of the arguments passed to the method when it is called. Yeah, they're also called dummy arguments because they're like placeholders. If the method has no parameters, then the parameter list will be empty. Methods that have a return type or other than void return a value to the calling routine using the following form of the return statement. Return value. Alright. Here, value is the value returned. That's different from the other one. Remember that the other use return will just escape to the calling software, whether it's a runtime program or whatever. But here, the return it doesn't escape. It produces a result. In the next few sections, you will see how to create various types of methods, including those that take parameters and those that return values. Adding a method to the box class. Although it is perfectly fine to create a class that contains only data, it rarely happens. Most of the time, you will use methods to access the instance variables defined by the class. In fact, methods define the interface to most classes. This allows the class implementer to hide the specific layout of internal data structures behind cleaner method abstractions, and that is called abstraction. In addition to defining methods that provide access to data, you can also define methods that are used internally by the class itself. Let's begin by adding a method to the box class. It may have occurred to you while looking at the preceding programs by the computation of a box's volume. That the computation of a box's volume was something that was best handled by the box class rather than the box demo class. After all, since the volume of box is dependent upon the size of the box, it makes sense to have the box class computed. To do this, you must add a method to box as shown here. This program includes a method inside the box class. Again, I'm not going to analyze it. Just going to show it for the sake of the video, so just pause as you need. Okay. So there we go. Next page. This program generates the following output, which is the same as the previous version. Look closely at the following two lines of code. mybox1.value, mybox2.value. The first line here invokes the value method on mybox1. That is, it calls value relative to the box, to the mybox1 object, using the object's name followed by the dot operator. Thus, the call to mybox.value displays the volume of that box defined by mybox1. And the call to mybox.volume displays the volume of the box defined by mybox2. Each time volume is invoked, it displays the volume for the specified box. Alright. If you're unfamiliar with the concept of calling a method, the following discussion will help clear things up. When mybox.volume, mybox1.value is executed, the Java runtime system transfers control to the code defined inside volume. After the statement inside volume have executed, control is returned to the calling routine, and execution resumes with the line of code following the call. In the most general sense, a method is Java's way of implementing subroutines. There is something very important to notice inside the value method. The instance variables width, height, and depth are referred to directly, without preceding them with an object name or the dot operator. When a method uses an instance variable that is defined by its class, it does so directly, without explicit reference to an object and without use of the dot operator. This is easy to understand if you think about it. A method is always invoked relative to some object of its class. Once its invocation has occurred, the object is known. Thus, within a method, there is no need to specify the object a second time. This means that weight, height, and depth inside volume implicitly, implicitly refer to the copies of those variables found in the object that involves volume. Yeah. Let's review. When an instance variable is accessed by code that is not part of the class in which that instance variable is defined, it must be done through an object by use of the dot operator. However, when an instance variable is accessed by code that is part of the same class as the instance variable, that variable can be referred to directly. The same thing applies to methods. Yep. Yeah, it's pretty cool, which is actually good to understand here. Okay. Because the method already has it. There you go. Yeah, the method itself is referring to the weight, height, and depth without the dot operator because it is within the class where they exist. That's what he's saying. Okay. Returning a value.